Alright, I think it's young. Okay, so last time we started talking about the axioms of set theory. We started axiomatically developing set theory. What was our first axiom? Our first axiom was that for any two sets x and y, x is in y is a proposition, meaning either x is in y is true or not x is in y is true. One and only one of those are true. Now, this first axiom introduces us to our two and only two undefined terms in set theory. That is what a set is and what this symbol is. This relation, this is a member of. So, we don't explicitly have set written here, but I told you this notation means for any set, or for every set. So for every set x and for every set y, either x is in y or not x is in y. One and only one of those is true. We have no definition of what a set is, it's an undefined term. We have no definition for what that relation symbol is, it's an undefined term. Just like points and congruence in geometry. You never define what a point is, you never define what congruence is. You just use those words to start defining other terms. Make sense? Okay, so now that we have our first axiom, which gave us some undefined terms, we can start creating some definitions in terms of those undefined terms, along with logic, right? We can always use logic, you can always fall back on logic. So I'm going to define this new symbol is not a member of, so x is not a member of y. How am I going to define that? I'm going to define that as not x is a member of y. Make sense? Next definition, x is a subset of y. I'm going to define that as for all sets A is in x implies A is in y. If it's true that A being in x implies A is in y, or every element in x is an element of y, then x is a subset of y. That's what we mean. Make sense? Alright, next one. X is equal to y. What does it mean for two sets to be equal? That means x is a subset of y and y is a subset of x. If everything that's in x is in y and everything that's in y is in x, then the two sets are equal. Good? Not equal, that's exactly what you think it is. That means not x equal y. X is not equal to y. This last one is probably the weirdest of these three. X is a proper subset of y. What does that mean? That means x is a subset of y and x is not equal to y. So they're not the same set. Notice that x is a subset of y up here. It's okay if they are the same set. X is a proper subset means x is a subset, but they're not the same set. So the way that we intuitively think about that is x has less elements than y, and everything in x is in y. So the set 1, 2 is a proper subset of the set 1, 2, 3. Make sense? Okay. So that was a bunch of definitions that we got from our first axiom, then we moved on to our second axiom. Our second axiom is our axiom that tells us that there is an empty set. There exists some set x such that for all y, y is not in x. X contains nothing. There exists some set x that contains nothing. Make sense? And then with that axiom, we did this proof that the empty set is unique. There's one and only one empty set. So we proved that there exists one and only one x such that for all y, y is not in x, and we denoted it with this special symbol, circle with a line through it. You good with that? You remember that? Ringing some bells? No? There's one and only one empty set. So we had an axiom, axiom 2 said that there is such a thing as an empty set, and then we did a proof last week that the empty set is unique, that there's one and only one empty set. It's a very similar thing to what we do with the axioms for arithmetic. One of the axioms for arithmetic is that every number has an additive inverse, and then we do a proof that every number has one and only one additive inverse. We did that in logic. And we call that one and only one additive inverse, it's negative. So there's one and only one number I can add to x to get 0, we call it negative x. There's one and only one number I add to 3 to get negative 3. To get 0, thank you. Negative 3 is that one and only one number, such that when you add it to 3, you get 0. That's how we define our negative numbers. Or that's one way we can do it. Anyways, so we proved that there is one and only one empty set. So we knew that there was at least one empty set, then we proved that there was only one empty set. Okay? Our next axiom. What does our next axiom say? Our next axiom says for any two sets, there exists some third set that contains those two sets as its elements. That's what this is saying. So we'll go over this again, but first I want you to get the intuition. We're saying for any two x and y, there exists an m whose elements are x and y. That's what this is going to say. So let's go over exactly what this says, make sure you understand it. For all x, for all y, there exists an m such that for all a is an m if and only if a is equal to x or a is equal to y. It's kind of dense, but once it clicks, it clicks. Should we say that one more time? Yeah. Okay. For all x, for all y, there exists some m such that for all a is a member of m, a is in this set m, if and only if a is equal to x or a is equal to y.
Okay.
A is in m, a is in here, if and only if a is equal to that thing or that thing. So for any two xy, there exists a set m such that a being in here implies a is equal to x or a is equal to y. Well, not just implies, if and only if. Good? We understand this dense notation here? Those of you who took logic I'm not worried about, but the rest of you? Alright, and we denote it like this. So now, notice that this is the first time that we introduce this type of notation. This is how you were used to seeing sets when you develop what we call naive set theory, where we just give you a childish set theory that you can start playing with without getting into the nitty-gritty. But now this is the first time that we've introduced this type of notation. So now we can start doing curly braces with two sets in between. And that's now a set. Good? Okay. Then we did this proof. The set xy is equal to the set yx. This gave us the property that we know sets have, that order doesn't matter in sets, right? That's what you're told when you're developing naive set theory, is that order doesn't matter. Well, we proved that those two sets are equal.
You proved that with those axioms?
Yeah. If x is equal to y, how do you prove two sets are equal? You show they're subsets of each other. How do you show they're subsets of each other? You grab an element in here, show it's in here, then you grab an element in here, show it's in here. Pretty simple. If a is in here, then a is equal to x or y, then a is equal to y or x, then a is in here, and then reverse. Good? Okay, then we have this definition for an ordered pair. The ordered pair xy we define in terms of sets, x, comma, the set containing x and y. Notice that if I were to give you this, 1, 1, 2, you unambiguously know that this is the ordered pair 1, 2, and not the ordered pair 2, 1. Right? So that's how we can encode an ordered collection from an unordered collection. So sets are unordered, but this is 1, 2. This is not 2, 1. Make sense? So that's how we encode our ordered pairs. We didn't do this proof. The reason we didn't do this proof is because it's really, really simple when you have this last axiom to do it. So just introducing it to you, it makes fairly intuitive sense. It's messy to prove without the last axiom, so we didn't bother proving it. But what is it? The ordered pair xy is equal to the ordered pair ab if and only if a is equal to x and b is equal to y. Make sense? Yeah. You already know this from, or you already introduced this in basic algebra. We use ordered pairs to represent what?
Points.
Points are a common example where we use ordered pairs. The point 1, 2 is not the same thing as the point 2, 1. Right? The only way that xy is equal to ab is if x and a are the same number and y and b are the same number in the context of points in R2. Then we create this definition. So we know the notation when we have one element in a set, or two elements in a set. What about this kind of notation? Is this defined? Can we just take a set with one thing in there? Yeah, now we can. So now we've defined what it means to have these curly braces with one thing in there. It's just x comma x. I know that I can create this set from Axiom 3, right? Axiom 3 says for any two sets you pick, you can put them together in curly braces. There's nothing that says I can't just pick the same set twice. So this is now well defined, and now I'm going to define this to be this. This is how we get the idea that duplicates don't matter in sets. So when you develop naive set theory, they tell you order doesn't matter in sets and duplicates don't matter in sets. Okay, so far we have the necessary information we need to know that's true. Good so far?
Yeah.
Okay, now I just want to make a note here that we're going to use later. Just remind you of this notation real quick. That we defined the symbol there exists x such that p of x to be not for all x, not p of x. So we're going to come back and use this later, but let's just make it make intuitive sense. If I say that there exists a duck that's pink, that means it is not the case that for all ducks, a duck is not pink. Did I say that weird?
No, that was right.
No, you did it right.
There exists a pink duck. It is not the case that every duck is not pink.
Is this just a rule of logic?
This was our definition for what we mean by the there exists. So remember, we just said, for all x, p of x, we said that if p of x is a predicate, then this is a proposition which evaluates to true if p of x is always true, otherwise this evaluates to false.
Okay.
So we defined this symbol, what we meant by this, and how this is a proposition, and then we define this one in terms of this. Right? Because we can take something that's now defined, and we can add logic to it all we want. Remember, you can always use your logic to create another definition, and that's how we define this. And intuitively, they capture the notion for every x, and there exists x, which we've all come across, right? Just quantifiers. Any question on any of those? Should all be reviewed thus far. Nothing new so far. So if you're like, I don't feel good about it, but I don't want to take class time, if you just go rewatch the lecture from last time, this is all material that we covered. And then the last axiom that we covered last time was the Union Axiom. So, kind of a mouthful, but what it says is pretty simple. So, for every x, there exists an m. Let's say intuitively what we're saying here. If you have a set x, I can union up all the elements in x and get this set. Make sense?
No.
What's the union of A, B, of the set, of this set with this set?
A, B, C.
Just this set.
Right.
So this axiom is going to tell us that if I have a collection of sets, there exists a set which is the union of all those sets. The union axiom. So that's what it's going to say in this definition. This thing over here is going to be M. This whole set is going to be X. And these sets right here are going to be S. And then Y is going to be the individual elements of this, or the individual elements of this. So let's go over the definition, or the axiom. So the axiom says for every X, there exists an M, such that for all Y, Y is in M, if and only if there exists some set in X that Y is in. Another way to say it intuitively, what are the elements of M? The elements of M are the elements of X. Something is in M if and only if there's a set in X that contains it. Y is in M if and only if there is a set in X that contains Y.
Yes, makes sense.
Is this notation quick enough for everyone? Should we say it one more time?
You could just use your A, B's, and C's. Just say A is your X, or A, B is your X.
No, this is your X. This whole set is your X. This set is your N. These sets are your S's. And then these A, B, and C are your Y's.
Right.
So A, B, and C are in the set N if and only if there exists some set S containing the A's, B's, and C's.
Right.
Where S was in X. Do we feel like we got this notation? It's pretty dense, but you gotta learn to just get comfortable with it. Because it helps us communicate shortly exactly what we're talking about. Okay, so that was the fourth axiom, the union axiom. We denote that special set M as the union on X, or the union of X. So then we have this special definition now. What do we mean by the set ABC? We mean that to be the union on the set AB and C. Remember that we know that AB is a set. That we get from our pair axiom, axiom 3. Axiom 3. We know that C is a set. We get that from our definition down here. We know that the set containing two sets is a set. And now we've just defined this set in terms of a set containing two sets. It might seem kind of pointless that I keep stressing that we do actually have sets, but it's kind of crucial to understand that the sets we're talking about are actually sets. Because it's real easy to get stuck in set theory, like we showed last time, to start talking about things that you think are sets, and that turns out they're not actually sets. Right? Remember we talked about the set of all elements that don't contain themselves as an element? And we showed that that kind of set can't exist? You remember that? Mm-hmm. No? Go watch it. It's right at the start of the lecture. Okay. So, we define the set ABC to be the union on these two sets, which we know is a set. We know that their union is a set based off of axiom 4. Therefore, this is a set. And here's the notation for it. Okay. In general, when we have A1, A2, all the way to n elements in a set, we define that to be the union of the first n-1 elements with an. This is a recursive definition. Right? So if I wanted a 5-element set, that's the union of a 4-element set with a 1-element set. But what is a 4-element set? That's a union of a 3-element set with a 1-element set. But what's a 3-element set? That's right here.
Right.
So it's all defined.
Okay.
That's cool.
Okay, recursive definition. All right. So now we can start writing sets the way that we're used to writing sets, like we have written right here, and we don't have to worry about it. Yep, that's a set. We're good. As long as we know that the numbers in there are sets, but remember I said we're going to kind of ignore that kind of stuff when we're talking about examples.
Right.
My examples aren't going to rigorously follow from the material we developed. They're just to help you understand the material. Okay. So our next axiom, axiom 5. So axiom 5 is going to introduce two things that we don't have defined. So we're going to read it, then we're going to go back and get the definitions for the things I was talking about, then cover it again. And we just split these two definitions out of it so that it's not just one big mouthful of an axiom. So let's cover it. So let R be a functional relation. What's that? We'll find out. And let M be a set. Then the image of R under M, written this way, the image of R under M is a set. Intuitively, what are we saying here? We're saying the image of a function is also a set. That's intuitively what we're saying. So let's go down and define a functional relation. A relation R, what's a relation?
Two certain unordered pairs.
No.
It's
In discrete math, you say it's a set of ordered pairs, but in this class, it's what?
When there's two variables and they're like connected.
There's two variables and they're like connected. They're like connected in what way?
Like with
So when we were developing logic, we talked about two terms back and forth. We talked about propositions and predicates. So if a predicate takes two variables, then we call it a relation. What's a predicate?
a statement that is true.
No, that's a proposition. Proposition is something that's either true or false, not both. What was a predicate?
It's
Something. A predicate is something that takes a variable and evaluates to a proposition. We called it a propositional valued function, is what a predicate was. A predicate takes a variable and spits out a proposition. Or it takes two variables and spits out a proposition, or three, it doesn't matter. Takes some number of variables, spits out a proposition. Right? What's an example of a predicate?
the uncle?
Huh?
Is the uncle of?
Is the uncle of? Sure. Is the uncle of is a predicate. You need to give it two people, and then you can evaluate if it's true or false. Laura is the uncle of Jacob. That's false. But is the uncle of by itself, we can't call it true or false. It's just a predicate. It's not until you give it variables that it becomes a proposition.
Wait, so that's just a sentence. Meaning, remember when we defined a sentence to be true? A statement, I meant, totally. It's a
So
statement.
don't be confused with how we develop logic from logic. And remember how we did it in this course. So we can't go through talking about like sentences, sentential connectives, truth functional sentential connectives, all that. We did that in logic to fully develop logic. In this class, we just started with propositions and predicates, gave them their definitions, and went with it.
But a proposition is very similar to it.
A statement is a proposition.
Okay.
Yes. Okay. So, a relation R, a thing that takes two variables and spits out true or false, a relation R is said to be functional, provided that for every x, there exists one and only one y, such that x is related to y. And this is exactly how you're used to talking about functions in math. When is something a function? If every input has one and only one output, then we call it a function. That's the same intuition that this is capturing. So R, the relation R, is said to be functional if for every x, there exists one and only one y, such that x is related to y.
Right.
So the same x cannot be related to two different y's. It can only be related to one. So the example of the functions that you're used to in math was something like f of x is equal to x squared, because it passed what you called the vertical line test.
Right.
But when you try to do it with f of x is equal to x to the 1/2, we ran into a problem. Right? Because this has two solutions, plus or minus the square root of x. Same thinking. If you're getting confused from this, and this already makes sense, don't worry about it. That's just for people who are used to like trig maths. Would have seen a lot of functions like that. Anyways, so relation R is said to be functional, provided that for every x, there exists one and only one y, such that x is related to y. Make sense? Okay. So that was what we meant by a functional relation. Now let's get to the next part. So let R be a functional relation, then the image of R under M consists of all those y's for which there is an x in M such that x is related to y. You're used to thinking about this as it's all the right-hand elements. It's all the outputs you get out of the function. It's all the y's. That's essentially what this is saying. Let R be a functional relation, then the image of R under M is all the things that M maps to. So if M is equal to 1, 2, and we're thinking about the function f of x is equal to x squared, then the image of f of M is going to equal 1 and 4. All the things that this function maps those elements to. It maps 1 to 1, it maps 2 to 4. Make sense? That's essentially what this is saying. So let's go over it one more time with exactly what it's saying to make sure you understand. Let R be a functional relation, then the image of R under M, M is just some set, the image of R under M consists of all those y's for which there is an x in M such that x is related to y. It's all the y's that get mapped to from some x where x is an element of M. It's all the y's that get mapped to by our relation from M.
Right.
Making sense? Okay, so now let's go back to our axiom and make sure it all makes sense. Let R be a functional relation and let M be a set. Then the image of R under M is a set. So we're saying whatever this image thing is, it is also a set. We've always just called it a set. You're used to just calling the image of a function a set. This axiom guarantees us that the image of a function is actually a set. So you take a function, you give it a set, it spits out a set. That's what the axiom says. Does that make sense?
No.
Am I stressing this too much? No, it doesn't make sense?
That was sarcastic.
Oh.
No, it makes sense. Why do you use the word image though? Why don't you just say that in notation, or is that pretty much the same thing? Why
What?
do you use the word image?
Image is just common vernacular for it.
Okay.
The less common one is range, the range of the function. But we usually say image.
I have a question.
Go ahead.
So in your definition of a relation, when you say for all x, is that just all x ever, or is it all x part of the set that the relation is on?
Yeah, so right now it's for all x ever, and you need to scope it if you want it to be a function on a set. Make sense?
Okay, yeah.
Alright, so now let's get some useful notation and then we'll do the proof that this axiom is leading up to. We very rarely use this axiom directly. We use this axiom to prove something useful, which is what we typically use. Basically, you're used to set builder notation, right? The set of all x such that some condition about x.
Yeah.
You know set builder notation?
Somewhat, yeah.
Let's give an example. Set builder notation. I say the set of all x such that
Yes.
x is greater than 2.
Yeah.
You've seen stuff like this all the time. So we're working up to trying to get this kind of notation for building sets. That's as unintuitive as it seems, what this axiom is going to give us. It gives us more than just that, but typically what we use this axiom for is that set builder notation, except for we'll see how that set builder notation is only a part of naive set theory and we have a small restriction. But we'll get there. So that's what we're leading up to, set builder notation essentially. Two definitions that are going to help us real quick to do our proof. So the first definition is, for all x in a set, something about x. Now you might be saying, didn't we already do this? No. All we've had to find so far is for all x, p of x. Now we want to say, for all x in a set, p of x. So we want to scope this x. So now this x isn't talking about for all sets, it's talking about for all sets in a set.
Okay.
Make sense? So, what do we mean by for all x in y, p of x is true? We mean that for all x in any set, if x is in y, then p of x is true. If I say for all x in y, p of x is true, that's the same thing as saying for all x, if x is in y, then p of x is true. That's what we're defining it to mean. This is a definition. Good? Anything confusing about that? Okay, so now we're going to use this over here. There exists x such that p of x is the same thing as not for all x, not p of x. We're going to use that to come up with what we think this should be. What do we expect this to be? There exists an x and y such that p of x is true. Ultimately, those of you who did logic are going to be used to converting that to this. There exists an x such that x is in y and p of x is true. That's the same thing as there exists an x in y such that p of x is true. There exists an x such that x is in y and p of x is true.
Yeah.
That's what we're going to lead to. It makes intuitive sense already, right?
Yeah. Mm-hmm.
And then let's just go through the proof using what we already know. There exists x in y such that p of x, this is logically equivalent to, when we want to switch our existential to a universal, we put a not in front and we not what we're doing it on.
Right.
And that switches our existential to a universal. Then, let's see what we got. Oh, now we're going to use our definition up here. For all x and y, something about y is the same thing as for all x, x and y implies that thing about x.
Right.
So going from here to here, we're just using this definition. Is everyone good going from here to here?
Yes.
That part ends up at the right side of the implication arrow. So whatever's in the parentheses ends up at the right side of the implication arrow. And then the for all x, x and y becomes for all x, x and y implies. So that goes at the right side of the implication arrow. That turns into that. We still have a not in front. We still have a not in front. Okay. This to this. Oh shoot. We didn't talk about x implies y is the same thing as not x or y. Should have done a refresher on this before I did this proof. So, when is an implication true? When do I know that x implies y? If the antecedent is false, we know it's true, right? False implies anything is true. So we know that x implies y is true when the antecedent is false or the conclusion is true. So x implies y is the same thing as not x or y. The antecedent is false or the conclusion is true is the same thing as x implies y. Is everyone good with this little tautology? Those two are logically equivalent. That and that are logically equivalent. Okay. Sorry, I should have done like a truth table or something for that before this proof, because we need to use it in proof. Okay, so that's what I'm doing here. X implies y is the same thing as not x or y. You see it?
Yeah.
X implies y is the same thing as not x or y. Now, when you factor out a not, you turn your ors into ands, right?
Mm-hmm.
When you distribute the not, you would turn the and into an or. If you factor it out, you turn the or into an and. Good? And then finally, back to this definition. Not for all, not some condition, is the same thing as there exists with that condition. Not for all, not some condition, is the same thing as there exists for that condition. And we're done. Good? So a lot of work for something that you intuitively already understood. Okay, ready to continue? Okay, so here's the hardest proof that we're going to come across today. Let's go over what we're trying to prove and then the proof. So if P of x is a predicate and M is a set, then the elements of y in M, such that P of y is true, constitutes a set. In other words, if I know that M is a set, and I know that P of x is a predicate, then I know that I can take all the elements y in M such that P of y is true and get a set.
Seems like it's the same thing we said over there. Down.
Same thing we said where? You're saying Axiom 5?
Yeah, well, no, if you have x in a set that satisfies a proposition.
Here's what it's saying. Let me give you an example. If I know that 1, 2, 3, 4, 5, 6, 7, 8, if I know that this is a set, and I know that is even is a predicate, then I can now take all the elements in here that satisfy this predicate, and I'm guaranteed that they'll be a set.
Wow.
That's what I want. That's what set builder notation allows us to do. I want to be able to use this type of notation. I want to be able to talk about all the y in n such that some condition about y is true. That's what this proof is for, so that we can start using this notation.
Why are we so scared about things not being sets?
Because, going back,
Right.
one of the sets that gave us trouble was the set of all elements that don't contain themselves.
Okay,
Why isn't that a set?
because it doesn't contain anything.
contains all the elements that don't contain themselves.
Well, there's no such thing. Oh, actually that's.
So why it's not a set was not intuitively obvious. People got stuck on this. There was a paradox. Until we realized how this axiom needs to be stated. X and Y are a set if and only if. So this being true, if and only if X, Y are sets. Was the way that we said it last time. X and Y are sets if and only if X and Y is a proposition. So it's not obvious when we are and are not talking about valid sets. Because intuitively, it feels like we should be able to put a bunch of objects in a set that, whoa, maybe you can't do that. And so, when we tried to do the set of all X such that let's see, it was a set of all X where they don't contain themselves, where X is not in X. We tried using this set builder notation this way, when you have to do it this way. You have to take the set of all things in a set that satisfy a condition. So we're showing that this is how you can do set builder notation, and trying to do this is actually bad. And it's not obvious that this is bad. And all your books, when you learn set theory, they show you set builder notation this way, they don't show it to you this way. So you're even taught to do it a way that technically enables you to build things that aren't sets. So, that's what this proof is trying to get to, is that when you take all the elements in a set that satisfy some condition, you're guaranteed to still have a set. That's what we're proving. And we're going to use Axiom 5 to do it. You understand at a high level what we're trying to do? Let's read it one more time then. If Px is a predicate, something that evaluates to true or false, you give it a variable, it says true or false. So if Px is a predicate and M is a set, then the elements y in M that satisfy the predicate constitute a set. And we denote them, the set of all y in M, such that P of y is true.
Makes perfect sense.
Okay, so let's do the proof. 1, let P of x be a predicate and M be some set. 2, then either there is some y in M that satisfies the predicate or there isn't. We're going to handle 2 conditions.
Okay, yeah, makes sense.
If there is no such y in M, then the set of all y in M that satisfy the condition, we'll just define to be the empty set.
Okay.
Right? We're trying to make sure that this notation always gives us a set. When there is no y in M, such that the condition is true, we're going to just call this notation the empty set. Now, when there is a y in M, we need to make sure that this notation captures a set. You with me?
Right.
Okay. So now, assume that there is some element in M that satisfies the condition, we'll call it Z.
Right.
Now, remember what Axiom 5 gives us. It gives us that the image of a functional relation is a set. So I need to construct a functional relation where the image is this, and then this will be a set. That's intuitively what I'm trying to do here. So, let Rxy, we're defining a functional relation. How am I going to define it? If the condition is true for x and x is equal to y, then we evaluate to true. Or if the condition is not true for x and y is equal to that z that happens to be true, then we include it. Otherwise we don't.
Go over that whole line again, please.
Yeah, this is dense, so what we're going to do is we're going to come down here, we're going to construct what it's talking about, and then go over this line again, because it's hard to just absorb the line. So let's come down here. Let's think about n being 1, 2, 3, 4, 5, 6, 7, 8, and let's think about p being the predicate is even.
Right.
Now we want to check to see the xy's that are in R. Xy's in R if this evaluates to true, right?
Mm-hmm.
x is related to y, or they're in here, for those of you who know relations as order sets, if this evaluates to true. Otherwise, they're not in the relation. Right? So let's try it. So, 1, let's see. 1, is 1 even?
No.
No. So 1 is not even.
Right.
So we're going to pair with it z. Oh, so first we need to get our z. So if there is no such blah blah blah, assume that there is some z in n that satisfies it. We're going to call that thing 4. Notice 4 is something in here that satisfies it. Right? So now, come back down here. So Rxy, what elements is that talking about? What pairs is that talking about? So which x's are related to y by this relation? The ones where x is equal to y and p of x is true, or p of x is false and y happens to equal z. So 1,
4.
so when x is 1, this is false, so we're not using this one. This is true, so y has to be 4. 1, 4 is in the relation. What about 2? Let's see, 2. Is 2 even?
Yeah.
Then y equal to x would be in there, so 2, 2. 3. Is 3 even? No, so it's over here, so 3 can only be paired with the z that we have, which is 4. So 3, 4 is in there, and then 4, 4, and then 5, 4, and then 6, 6, and you see the pattern, right?
Right.
If the x was in there, if x satisfies a condition, pair it with itself. So 2 satisfies the condition, pair it with itself. 4 satisfies the condition, pair it with itself. 6 satisfies the condition, pair it with itself. Otherwise, if it doesn't satisfy the condition, pair it with the thing we know satisfies the condition. Right? So I'm going to pair all my odd numbers with 4, and I'm going to pair all the even numbers with themselves for all the things in n. Alright, so now let's look at the image of this. The image is all the right-hand values, right? What's the image of R going to be? 2, 4, 6, 8. We'd eventually get 8 in there, right? 8 is going to be in there. So all the right-hand elements is just going to be all the evens. So we know that all the right-hand elements are a set due to axiom 5. Therefore, the set of all y, where y is even, which is equal to the set, we know is a set.
That's actually really cool.
That's how we're doing this. And I know that this is kind of a headache to look at the first time. I had to stare at that for like 5 minutes before it finally clicked in my head.
Just putting all the odds in one bracket. Pair it to one thing that satisfies the predicate.
Yeah, you're pairing all the things that don't satisfy the condition with something that does, and all the things that do satisfy the condition with themselves. And then you're taking the image of that relation, which is going to be all the things that satisfy the condition,
Which is going to be a set.
which we now know is a set. So that's what this is saying. So let Rxy be this thing. Observe that R is a functional relation, right? X is always paired to one and only one thing. It's either paired to itself or it's paired to z. There's no way to evaluate this and pair x with two things.
Right.
So since that is functional, then its image is a set, which is what we mean by this notation. So this notation, in either case, captures a set.
I wasn't here last time. So I need to really go back and watch that video.
All right. You feel like you kind of understood the proof?
Yeah.
Hopefully this helped, because once I drew it out, it became obvious to me what it was saying. All right. So now we know that we can use a set builder notation like this. Notice we can't say the set of all y such that p of y. That's not necessarily a set, but we can say the set of all y in M such that p of y. Good? So that's how we can use our set builder notation. So now we know we can use that notation. All right, a couple definitions now. So remember we had the union of the sets. Naturally we want the intersection of the sets now. So what's the intersection on X? It's the set of all A in the union of X such that for every set in X, A is in that set. So A is in the intersection of X if and only if it shows up in every set in X. Does that make sense? Let's come down here and do the example and then go back up and look at it.
Okay.
Okay. So we're looking at this one, this example. So we're going to do the intersection on the sets X, Y, and Z, where X is 1, 2, 3, 4, Y is 2, 4, 6, Z is 3, 4, 5, 6. Okay? The intersection on X, Y, Z is the set of all elements that show up in X and in Y and in Z.
4.
4.
Okay.
Right? 4 is the only element that shows up in there, and in there, and in there. So let's read the definition one more time. The intersection of X is a set of all A in the union of X, such that for all the sets in X, A is in that set.
Okay.
Oh,
That makes sense.
yes.
You're used to seeing it like this. It's the set of all A such that for all Y in X, A is in Y.
Yeah.
You're used to seeing it like this. It's a set of all A, where A is in Y, and Y is just a member of X. But we can't use this type of notation. We need to specify what set A comes from. A comes from the union of all these. So we're saying A comes from the set containing 1, 2, 3, 4, 5, 6, 7, 8, or 1, 2, 3, 4, 5, 6, right? Maybe we should have done this one first. Let's do the union. What's the union of X, Y, Z?
1, 2, 3, 4, 5, 6.
Is there anyone confused by why this is a union of those? It's the set of all the elements that are in a set inside the set we're unioning. It's the elements of this set. Okay? So, now on the intersection, we're saying the intersection of this set is all the A's in here that show up in all these. It's the set of all the A's in the union of X, such that for every set in X, A is in that set. Does that make sense?
Mhm.
You understand why we need to write it this way and not this way?
Yes.
Because this isn't guaranteed to be a set, this is guaranteed to be a set. Good? Okay. If the intersection on X is equal to the empty set, then we call the elements of X mutually disjoint.
Which makes sense.
Which means that they have no elements in common.
Right.
So if I were to just do, all of those have an element in common. If I were to get rid of 4, no, that's not right.
Yeah.
I wrote a definition wrong.
Should be like, whatever it grows.
That is not mutually disjoint.
Sorry, we're mutually disjoint.
Let's see. We just did Axiom 5. Oh,
She wouldn't have looked it up because she would have left it.
if that is equal to that, where X is equal to a 2-element set AB, then A and B are disjoint, is all it says. Okay, if X has 2 sets in there, and when you take the intersection on it, you get the empty set, then the 2 sets A and B are called disjoint. In other words, they have no elements in common. If 2 sets have no elements in common, we call them disjoint. Good? Sorry about that.
Is it only 2 or can it be 3 as well?
Only 2 when you're talking about disjoint.
Okay.
And then we have a notion of, if I have a set of sets, A, B, C, and for any two you pick, they're disjoint, then the whole collection is mutually disjoint.
Oh, okay.
So that's why I got confused. That's what I get for just reading off my paper and writing instead of looking at while writing. Okay. Next, set difference. X minus y. This isn't algebraic minus. This is when you have just two sets that you're subtracting. So the set x minus the set y is equal to the set of all a in x, where a is not in y. So take your set x, remove all the elements that are in y, whatever you're left with is what the set difference is. When you look at a Venn diagram of it, if this is x and this is y, then x minus y are the elements over here.
Okay.
Okay, and then we already made this note, strictly speaking, the set of all x such that some condition about x is not allowed. Now, sometimes it becomes very, I don't think we're ready to have that discussion yet. I should have put that lower. We'll come back to that. Axiom 6. Axiom 6 is a power set axiom. For those of you that know the power set, it just says every set has a power set. That's all it's saying. So, the power set is a set of all subsets. Take a set, look at the set of all subsets, that's the power set. Let's write out the power set first, and then we'll come back to this. So let's look at the set x is equal to AB. Then the power set of x is all the possible subsets of the set AB.
Oh, would it be A, comma, AB?
So first off, the empty set's in there. The empty set is a subset of this, right? Everything in the empty set is in there. There's nothing in the empty set. Right? The set containing A is a subset. Everything in this set is in that set. Therefore, this is a subset of this. The set containing B is a subset. And then finally, the set AB is a subset of the set AB. Every set is a subset of itself. What does it mean for x to be a subset of y? It means everything that's in x is in y.
Right. They can be equal.
Right, so they can be equal. Everything in here, the set AB, is in here, the set AB, right? So these are all the possible subsets you can get from this set. The set of all possible subsets is what we mean by the power set. So what the axiom is saying is that when you have some set, the set of all its subsets is also a set. That's what the power set axiom gives us. So now, let's say it. For all x, there exists a y, namely the power set, such that for all sets u, u is in the power set if and only if u is a subset of x. For all x, there exists y, such that for all u, u is in y if and only if u is a subset of x. So if u is a subset of x, then it's in y. If u is in y, then it's a subset of x. Does that one make pretty intuitive sense? It's not near as big as some of our definitions. We denote y, the power set of x, by fancy px. It's common notation for the power set of a set. And we call it the power set of x.
We're defining the power set right now.
The axiom gives us that every set has a power set. The axiom gives us that for any set you pick, there exists some set y that satisfies this condition, and we're using this notation to capture that set y.
Can we clear this up real quick?
Yeah.
When we use x's and y's, are we always talking about a set?
We're always talking about sets.
Okay. And when we use a's and b's, we're talking about variables.
When we're using a's and b's, we're talking about sets. When we're using any variable, we're talking about sets. Every mathematical object is a set somehow. Give me a mathematical object.
A pyramid.
Well, that's not really a mathematical object. You can talk about the mapping of a pyramid as the sets of points. Points are just ordered pairs. We have our definition for ordered pairs. We put all those ordered pairs into sets for the sets of all the lines, or however you want to capture the pyramid. pyramid, there you go, is just a set of some sort. It's a set of sets, a set, a set, a set, a set, a set, a set. It's all sets, all the way up.
Okay.
So yeah, everything here, we're always talking about sets. Going back to our very first axiom, x and y are sets if and only if this notation is a proposition. If x and y is true or false. Those were our only two undefined terms for building set theory, for building this, was set and this relation is a member of. Set is like points in geometry, is a member of, is like equivalent in geometry. Or congruent, not equivalent, congruent. You don't ever define what congruent means, you don't ever define what a point is. Similarly, we never define a set, but we're always talking about sets. We never define is a member of, but that's the only relation we use to define all our other relations. We defined all these relations, but notice they always come back to that. Okay. So, given a set X, we're guaranteed that its power set exists. So we have a set X, we can talk about the set of all its possible subsets, called the power set. Now, this is another place where, in naive set theory, we thought we needed this notation. We thought that we didn't need an axiom for the power set, and we could just define it this way. We could define the power set of X to be the set of all U, such where U is a subset of X. But nope, doesn't work. We have to have a power set axiom because we can't do this. Because we can't say all the U in what? What can I put there to define it this way? We don't have something to take these from. So we actually have to let the power set, its existence, be an axiom. Okay. And then I want to come up and talk about this. Strictly speaking, we can't talk about all the x such that p of x, but sometimes it's a mess to specify what set this is coming from, or it's obvious what set that's coming from. As long as we know what set this is coming from, we will use this notation. So for example, when you were doing all your Traeger algebra, you always did the set of all x such that some condition like x is less than 2. What did you really mean? You meant the set of all x in the real numbers such that x is less than 2.
Right.
So this is what this was shorthand for, and it was just understood that you were talking about in the real numbers. And you weren't talking about, I was going to say in the complex, but then we can't use less than like that. Anyway. So, now let's get to the Cartesian product. And this is where you're going to see why we sometimes admit the set comes from. So first off, intuitively, what is x cross y? It's all the ordered pairs that you can get where the first element comes from x and the second element comes from y. So let's do an example first, and we'll go over the definition. So if I want to do the set 1, 2, crossed with the set 3, 4, this is equal to the set 1, 3, 2, 3, 1, 4, 2, 4. The Cartesian product of two sets gives me all the ordered pairs I can make where my first element comes from the first set and my second element comes from the second set. Make sense?
Yeah.
Okay. So here's what it is. Writing it correctly. X cross y is equal to the set of all the ordered pairs in the power set of the union of x, y, such that A is in x and B is in y. Now, trying to wrap your head around this thing is not trivial, right? Because this is going to give you sets that look like this over here, which then enable you to start talking about A and B in there. Right? So here's actually how we're going to write it from here on out, and we're not going to bother with this dense notation. We're going to say that x cross y is equal to all the ordered pairs A, B comes from X, the first set, and B comes from Y, the second set. And that's what we mean by the Cartesian product. We already did all the examples except for X minus Y. So here's X, here's Y. What's X minus Y?
1, 3.
3, right? X minus Y is everything in X that's not in Y. Okay. Whew. 3 more axioms.
We need to move your camera.
Good call. Remind me to get some smiley faces. You just earned one.
Stickers in trash of teaching.
Good enough. Okay. Oh, 2 more definitions real quick that you already know. When we say X union Y, we mean that to be the union of X and Y,
First and second.
right? Are you all good with this? I mean, I imagine that you're a lot more comfortable with this and this than you are with this and this. The X intersect Y is the same thing as the intersection on X and Y. It's just some shorthand that we use since we use it so much.
Yes.
So are we good with these definitions or do we need examples?
We're good.
We're good. Okay, so now Axiom 7. Axiom 7 is the, what's it called? It's like the Axiom of Infinity, something like that. It basically gives us the natural numbers are a set. So let's write out exactly what it gives us, and we'll name the natural numbers as we go. So there exists a set X such that the empty set is in there, and for any Y, if Y is in there, then Y union the set containing Y is in there. So let's start building this. So what is X? First off, what's the first thing we know is in there?
0.
The empty set.
Yes.
We know that the empty set is in there. Okay. Now, since I know that the empty set is in there, then the empty set union with the set containing the empty set is in there. Right? For any Y in there, Y union the set containing Y is in there. So what is the empty set union the set containing the empty set?
1.
Right? Well, what is that?
The empty set.
The set containing the empty set. Take everything that's in there or in there, and what are you left with?
What's in
That
there?
doesn't make sense to you? Okay, maybe we weren't good with the union. What is the union of the set 1 unioned with the set 2? That's equal to the set containing 1, 2. What if I union the empty set with 2? What am I left with? 2. So if I take the empty set union with the set containing the empty set, I'm left with the set containing the empty set. What's the difference between that and this?
But the set and the set containing the empty set and the empty set are 2 different things.
Right. This is different than this.
So wouldn't it be? Oh, okay.
Is everyone good with these two? I mean, you remember that this and this are saying the exact same thing, right? And that's the same thing as this. Right?
Do that.
Just empty sets. Okay, so I know that this is in here. The set containing the empty set is in here. Okay? So now that I know that the set containing the empty set is in there, I know that what? The set containing the empty set unioned with the set containing the empty set is in there. What is this union this? What's in here?
The set containing the empty set.
Yeah, the empty set's in here and the set containing the empty set's in here. Right? When I union these two sets together, I take everything that's in this set, that's the empty set, and everything that's in this set, that's the set containing the empty set. Good? That's what's in here. Alright, now that I know that this is in there, I know that what else is in there? I know that the set containing the empty set containing, I know that this union, the set containing that I'm missing one. I know that this union this is in there. Right? So what is that? That's the set containing empty set. Did I get it all? Yeah. And we could continue this way, right?
Yeah.
So, this is what we define to be 0. This is what we define to be 1. This set is what we define to be 2. And this set is what we define to be 3. And notice some nice properties about it. How many things are in the empty set?
0.
0. How many things are in the set containing the empty set? 1. How many things are in 2?
2.
How many things are in 3? And if we continue on, there's going to be 4 things in 4, 5 things in 5, 6 things in 6. Another way that we could read these things is notice that 1 is equal to the set containing 0, right? 0 is the empty set, 1 is the set containing 0. And then 2 is equal to the set containing 1 and 0, or 0 and 1, sorry, follow the order. And 3 is equal to the set containing 0, 1, and 2. Right?
Right.
And that's how the pattern's going to follow. 5 is going to be the set containing 0, 1, 2, 3, 4. 5 is going to have 5 elements in it. And so, as a general rule, so this right here, this is giving us the natural numbers. If we keep doing this, this gives us 0, 1, 2, 3, 4, 5, 6, 7. So this gives us the natural numbers. We call this special set that we know exists the natural numbers. And then, it has some nice properties. We know that for every n inside this set, the size of n is equal to n. I'm using notation that we haven't defined yet, right? I'm just pointing things out that are nice properties that has. And also notice, we can now define the less than relation. X is less than y if x is in y. What are the numbers less than 3? 0, 1, and 2.
That is actually bad A.
So now we can use this is a member of relation to start defining less than. Right?
That is cool.
It is cool. And then I say as an example, 7 is equal to 0, 1, 2, 3, 4, 5, 6. So x is in 7 if and only if x is less than 7. Right? Okay, so that is how you would define the natural numbers. And it has those nice properties. So that's what Axiom 7 essentially gives us, is the natural numbers. Now you might naturally ask, okay, so do I need another axiom that then gives me the integers, and another axiom that gives me the rationals, and another axiom that gives me the reals? And the answer is no. You can actually construct the integers, the rationals, and the reals from the naturals.
Which we did in calculus.
No. We specifically didn't do that in calculus.
From the naturals?
We define in calculus everything as a subset of the reals. For example, in calculus we define the naturals as the intersection of all inductive sets.
I remember that, yes.
Yeah, so no, we didn't. We mentioned that we could do it that way, it just takes time to do it that way, and we want to just get going with the calculus. Okay. Our next axiom. Our next axiom, Axiom 8, is kind of a weird one. It's called the Choice Axiom or something like that. It has choice in the name. Oftentimes, set theory is developed without this axiom. I'm just giving it to you for complete set theory. It's the Axiom of Choice, that's what it's called, the Axiom of Choice. And let's go over what it gives us. So, if I have some set x, and the elements of x are mutually disjoint, in other words, none of the sets of x have any members in common, then there exists some set y, which contains exactly one element from each set in x. Where this is useful is hard to understand until you get comfortable with equivalence classes, which I don't know if any of you are. So I'll try and give an intuition for how this might help. So imagine I grouped all of you by your last name. So I did the set of all, and then A is all the people with last name A, B is all the people with last name B, C is all the people with last name C, D is all the people with last name D, and say we only had 4 last names in here for some reason. So let's say I grouped all of you guys into one of these sets. Notice that each of you would show up in one and only one of these sets.
Yeah.
So these sets would be mutually disjoint. If I took the intersection of any 2 of these sets, it would always be empty. No one is in more than one of the sets.
Right.
So let's talk about a case like this. So what the axiom gives me is that if I have these sets, then there exists a set containing one element from each of these sets. So I can take one person with last name A, one person with last name B, one person with last name C, one person with last name D, and I'm guaranteed that that's a set. Where it's useful is when I don't know how to distinguish any elements of these sets from each other. So all I know is you have the same last name, and I can't distinguish you outside of that. I'm still guaranteed I can grab just one of you from each of these sets, and it will end up with a set. If any of you are familiar with like a basis element, this would give us, no, never mind. If it comes up in our class, I think it should, then I'll try and drill home where it comes up so that you can see it in action. But oftentimes set theory is developed without it because it's used in kind of these one-off cases where you don't really know everything about the set you're dealing with. Next, last axiom, axiom 9, is a non-existence axiom, and it just stops us from trying to create certain types of bad sets. So what does it say? It says for every set that's non-empty, for all x where x is not the empty set, then there exists y, there exists some element in x, such that x and y have no elements in common. So for every set x, it has this member y. For every set x that's not empty, it has an element y, such that y and x don't have any elements in common. So for any set x, I can grab an element out of it, take their intersection, and get the empty set. So what that stops us from doing is creating sets like take the set x, take a set with x in x. We can't do this. Right? Because if x was in x, then I have an element in there, such that when I take their intersection, it's not empty. I just get x again.
They're not mutually disjoint.
So let's go over it one more time. For every set x, where x isn't empty, there exists a y in x, there exists an element in x, such that when I intersect x with that element, I get the empty set. Pick any set you want. Let's pick this set. If I take this element and intersect it with this set, what do I get? The empty set. If I take this element and intersect it with this set, what do I get?
Empty set.
In that case, I get the set containing the empty set. Right?
Oh, right.
So we're not saying if you intersect it with any of its elements, we're saying it always has an element in there, such that when you intersect them, you get the empty set. Does that make sense? Losing you? Well, if that makes sense, then that is the end of our development of set theory. We call this particular set theory that we've developed ZFC set theory. The Z and F are just the names of 2 mathematicians who developed all of them without axiom 8. C, we say ZF set theory with the choice axiom. With choice is how they say that. ZF with choice is what ZFC is. That means you include axiom 8. So if you want to continue based off of where we left off, so like you want to start developing arithmetic with these axioms, then you know how to Google it. Developing arithmetic with ZFC set theory axioms, or something to that effect. But this is as far as we're going with set theory. From here on out, we're ready to jump into topology. Unless you have questions, concerns, unless you're done, or you're burned out. You can nod. I won't get mad at you. Okay. If we're burned out, let's not push forward. I don't want to lose you. Yeah. So, go ahead.
Based off of these axioms, you said you can build any mathematics or just?
Yes, any field of mathematics could theoretically be constructed from just these axioms. So here we have the natural numbers. We could then develop an arithmetic function where, what would we mean by set A plus 1? You typically start out with a plus 1 function, an incrementing function. We just define that to be A union with the set A, like that. And every time you do that, you plus 1. Notice that's exactly what we were doing up here. We took this, then we unioned it with the set containing itself to get 3, and we do that with 4. And then you can define arithmetic in general. A plus any number B is doing this B times. So you can start developing arithmetic that way. Then we define integers to be sets of ordered pairs of naturals where the left hand is a positive term and the right hand is a negative term. So there's a bunch of ways I could encode -3, but one of them would be 0, 3 is one way we encode -3, or 1, 4 is another way that we encode -3. So you have to get into equivalence classes to start grouping numbers into one number, because these are the same number. And then rationals are just ordered pairs of integers. So when I have this rationals now, so if I have the rational 0, 3, comma, 1, 4, a rational is an ordered pair of integers. This is -3 over -3, which is 1. So here's one way that we would encode 1 in the rationalism, so you can keep building like that.
Are there different theories that can do the same thing with different axioms where they can build mathematics?
Yes and yes. So in two senses. One, you do not have to use these axioms for set theory, and you can still do it. So for example, another way for axiom 7 to be phrased is if y is in x and the set containing y is in x, and so then we define 0 to be the empty set, 1 to be the set containing the empty set, 2 to be the set containing the set containing the empty set. Typically we do it this way because you get some nice properties like the size of the set is just its number, and x less than y, you just have to look at the elements in there. But you can still do it this way and then define less than in a different way. So you can use different set theory axioms and still get something logically equivalent. And then there's also something called category theory, which is different from set theory altogether, which strives to do the same things. I don't know how far it's gone, and I don't know if it's been demonstrated that it's just as powerful as set theory, but
Okay.
yeah, typically this is what's used. Any other questions? What? All right. Well, if that's it, then we'll call it there, and we'll continue with chapter 0 next time.
Nice.
So excited.
Because
We'll finally be starting the actual textbook for those of you who
started it.
intended to get it.